friends, I'm so glad we can be together again, and I'm so excited that I can show you some of the miracles, the wonders of the water that will follow in this lecture. If it wasn't enough what we studied till this very moment, now I'm going to show you even more. And if you can see all of these beautiful laws that we studied, and obviously it takes little effort from your side to assimilate it and to think it over, but it's worth taking it. Definitely you're going to see all of this beautiful order and all of this, how all these things are nicely fitting together. So therefore they cannot just happen out of nothing. Obviously there is somebody that puts them together and finally tune them out of love of us so that we can live happily on this earth. Now you see on this picture a few things. You can see a big ship on the sea. That's the Indian Ocean just in front of my house, and also see a tree just behind my back, that tree, and also there is another one there. And you can see also clouds in the sky. Now you can see all over there is water. Water in the clouds, water in the air, water in the water, water in the trees, water in the speaker. The water is ubiquitous. So if we study the properties of water, actually we have to touch almost all chemistry and almost all physics. Do you see? So it is so nice that taking such a simple object we can discover so many things. In this lecture we're going to study exactly that. What's happening with the sea water, what's happening with different qualities of water. But now in the beginning I would like first to make sure that you know what I'm going to talk about, simply because I'm actually building on the previous lecture. If you didn't watch the previous lectures, please go back, start from lecture 1, do yourself a favor. Just watching it casually on the Sunday afternoon is not working. You need to be concentrated. All right, so do yourself a favor, start from the beginning. I will make now a short revision on what we studied in the form of questions. So if you struggle answering these questions, that means you don't know the material that was in the previous lectures. So better go and study. It will be better. Because if you don't study it, you won't understand what is now. And definitely, I promise you, your life is going to be completely different after I finish all of these lectures. You're going to know so much more, and it's going to be so much practical for you to know it. So you're not going to be enriched only intellectually by having more insight and more scientific knowledge, but as you can see, I always show practical examples so that your life is going to be practically much easier and much convenient after I finish these lectures than when it was in the beginning. Now let's start with the questions. Now you see here something very interesting. You see here there is a electrodes, there is a light, and there is a current going through. So now I'd like to ask you, there is a salt there in the glass. You can see the salt. You can see it straight there. There is a salt and there is electrodes. Right. Why salt is not conducting electricity? Salt, dry salt, as we're using it in the kitchen. But now look at it, what's happening if we put water, because we're studying water now in these lectures. Now if we put water, you can see the light shines. So now what happened and what makes actually the salt when it's dry not to shine, and when we put water it starts shining and quite bright. Now it is very good conductor of electricity when the salt is dissolved in water, but it's actually insulator, that means is not conducting electricity when there is no water. What do you think about? Please press the pause button and think about. We study it. You just need to come back to the lecture. So if you don't know it, that means you need to go back and study it. The answer is very simple. We studied that one of the very strong connections are ionic bond. And as you can see on this picture, you can see the ionic bond between sodium atoms and the chlorine atoms. Right. There is no free electrons. There is no free charged particles. Yeah. All of this staying in a very solid, nice lattice, as you can see. And this is why it takes a lot of temperature to boil this. I said 800 degrees. So there is no free electrons, but electricity is what? Can you tell me what's electricity? Electricity is a current of electrons. All right. So if there is no electrons to move, there is no current. And there is no electricity. Where is the free electrons here? Where is the free charged particles? There is nothing. Everything is in the lattice. Now let's see what's going to happen when we put water into the salt. Let's see what's going to happen. Now the water molecules, as you can see, the positive part of the water molecule, which is the hydrogen atoms, they turn to the negative part of this complex crystal structure. It's not molecule, this is actually a unit formula. As you can see, there is no covalent bonding. They don't share electrons. Just chlorine, because it's so strong, stole electron from the sodium. There is no connections. So now when the water surrounds the chlorine atom, and you can see the positive atoms, hydrogen atoms, surround the chlorine atoms, they tear it off. They tear it off from there, because the electric force now between the chlorine and the hydrogen atom is more than the electric force of attraction between the chlorine and the sodium. This is why it gets teared off. When it's stronger, it tears it off. So now, when it's teared off, it's still charged. It's still charged particle. Do you see it? It's still charged particle, even when it's teared off. Now, when it's teared off, what is happening? Also, the other part of the molecule of water, the negative part of the water, now it turns to the positive part of the salt unit formula, and that's the sodium. And the sodium is charged because he gave one electron to the chlorine. So now you can see all the oxygen atoms are turned to the sodium atom, because oxygen is the oxygen part of the molecule is negative and sodium atom is positive. Now we've got charge. Now when we've got charge like this, now when we've got charged particles, now we can conduct electricity. You see, now we can conduct electricity. Now the negative charge will go to one part, and the positive charge is going to go to the other part. So we're going to have current of charged particles, and that's electricity. But now you may ask a question. Hey, you told us that sodium is very reactive metal and chlorine is a poisonous gas. So now every time we put salt in the water, now we're going to have sodium and we're going to have chlorine and we're going to get poisoned and we're going to get all of this. No, that's not the case. Why it's not the case? You must answer me. Yes, correct. Because their valence shell is completely filled. There is a octet of valence shell. Sodium gave one electron and chlorine received one electron, so that their electron shell is like the noble gases. So now they don't react. You see? So they don't react. Everything is fine. But now, if I may tell you a story, and so that you can remember why the sodium chloride, the salt, conducts electricity when it's in the water and is not conducting electricity when it's dry. Now imagine that there was a guy on the name of sodium and there is a lady on the name of chlorine. So now they get attracted to each other because Mr. Sodium wants to give his electron to Miss Chlorine, and Miss Chlorine wants to take his electron. So now they get married and they made a nice house, crystal structure, and everything is happy. She's happy, he's happy. They get very close together because they are attracted to each other. It's very nice. But now imagine for a second that now they go to the beach. Now the beach is where the most family trouble starts. So now it starts an adultery now. So now what's happening when they go to the water is woman gets a lot of attention now. You see? Now he gets a lot of attention. You can see it there on the picture. There is a lot of attention for the woman. And now she gets disconnected from her husband, Mr. Sodium. She's get disconnected and now she commits adultery. You see? So now the man also start thinking, no man, I need some fresh oxygen. This woman is torturing me. She's committing adultery. And he gets some oxygen and he also commits adultery. So now both of them, their family is now destroyed. One commits adultery and another one also commits adultery. And this is why when salt is dissolved in water, we've got trouble. We've got start conducting electricity. Now, that's my first question. Let's go to my second question. Now you see here a lot of fish in the water. Now I want you to tell me why this fish breathes in the water. How it can survive breathing. Obviously there is something that keeps her alive. How she breathes. Well, if she's in the air, you know, she can breathe oxygen, but what she can breathe in the ocean? Yes, the oxygen is dissolved in water, and I want you to know why it's dissolved in the water. We studied this in the previous lectures. It's dissolved in the water because the water molecule is polar covalent. The oxygen molecule is just covalent, it's not polar. So now when they get to each other, the covalent molecule of oxygen gets attracted to the water because we start connecting them, these two, by inducing this bonding by the way of when the polar molecule is turned to one side to the non-polar, it is called dipole, induced dipole. So the water is a dipole, little magnet. But when there is a piece of iron, even if it's not magnetic, the iron is also attracted because it induces magnetism and it gets attracted to that. The negative of the water molecule turns to its negative part, that means the oxygen part repels the electron of the oxygen bond. But when it repels the electrons, then the positive charge, which is the nucleus, gets attracted to that. This is why the oxygen gets attracted to the water molecule, and this is why we've got the oxygen dissolved in water. That's my second question. Then I've got more questions to you, and that's my third question. Now look at it and tell me why blowing the soup, all right, cools it. When it's too hot, the soup, we blow it and it actually cools it. Why is doing like this? Now let me tell you, the temperature of the soup itself, you can blow as much as you want, you're not going to change it, the soup. But what's happening? There is a two process, and we study them. So, please think about what's going to be. Of course, blowing the hot soup actually cools it down through, not through cooling its temperature, but what's happening with two processes. There is a two primary processes. One is a convection. That means the hot particles, the vapor pressure goes up because it's lighter, and this lighter takes less volume. When it's less volume, the heavier volume of the cooler air goes down to the soup. This is why actually if you burn a candle, you're going to see these convections. If you put up water in the pot and start boiling it, we're going to have these convections. What's happening at the bottom, the water molecules get faster speed, they break the hydrogen bonds, and because of that, the water expands a little bit. They got faster things. They get lighter because they expand. The density gets lower. When they get lighter, they go up because the denser liquid actually takes its place. Now we've got the lighter went up and the cooler one went down. So you've got these circles. This is called convection. All right. This is why you can never have in the spaceship, you can never have candle, because the air there, there is no convection. Actually, there is no light and there is no heavy. You understand? In the spaceship, there is weightlessness. So now there is no light and heavy air. So now what's going to happen is when the light start putting hot air, there is air in the spaceship, otherwise they'll die. They need to breathe. When the hot air goes up, it gets lighter, but there is a weightlessness. There is no light and heavy there. So now there is no convection there, and that means when the candle burns, all the oxygen that is very near to each other is going to die. It's going to die off. But we're using convection on the Earth because of the gravitations that we have. But don't light a candle in the spaceship. So this is convection, the first mechanism. Convection involves this moving of air. So now when you blow on the tea or on the soup or whatever it is, the hot drink, actually you're removing the hot, lighter vapor, water vapor that's above that, and then immediately gets substituted with colder air. This colder air now, there is a gradient of temperature. One is cold, another one is hot. When it's hot, what's happening? The hot always wants to go to the cold. So now the fast moving molecules of water, they go to warm the colder, but they fly away. So now this air gets warmer with water vapor, it goes up. Now you blow again, you again remove the hot water vapor which is around it. Cold air comes back. Cold air comes back. So actually you start slowly cooling the soup, the temperature of soup, because actually you're removing the fastest moving water molecules. They go to the vapor phase and then you remove them. So that's what it is. And on top of that, the blowing on the hot soup actually increases the rate of evaporation. Because actually, you know very well, the hot water molecules on the surface, they carry heat away with them when they evaporate. Now, what about the fan? Can we cool ourselves with a fan? Yes, by the same reason. Actually, the fan doesn't cool the air, but what's happening, it removes the water vapor that is around, that you evaporated, and the heat that is around you, and substitute it again just like a blowing of the hot soup. So it blows it out and then the cold comes out. Now, this is why it's very important when you put the fan, you to open the window as well, or open the door, because you need to make a draft, a new cold air have to come. Unless outside is so hot, then you need to keep the, obviously, to close the window, maybe open it just little bit so that we can have air coming inside. And so you're gonna have this draft. So now what's happening is actually the fan, you know, when you take a hot air, you can actually by turning it, you can make it even hotter, but now it doesn't cool yourself in this way by turning it. Now it cools you out by removing the hot air around you and the moisture that's around you, and actually it comes the cold air, and now we've got more efficient heat transfer. Otherwise, when you start moving a hot air or hot liquid, actually any hot fluid, actually you're giving up more energy and actually gets hotter. This is why a very old medicine is when you get sick, you put your feet at hot water with salt to rise up a little bit the temperature, although it's very minimal. And then after, my granny always used to say me, don't move your feet because it's gonna get hotter. Oh, I'm sweating, it's almost a torture, but I'm sick, so I need to get well. So she says, don't move your finger, but now can a child stay still? So it starts moving, I feel more hot. So you see, moving creates more kinetic energy, and that creates energy as a heat, because kinetic energy of the molecules is actually faster kinetic energy, faster movement, it's hot temperature. Now the aircon cools you much better, and actually cools the air by expanding the gas inside. So when the gas expands, actually the gas does work against the atmospheric pressure, and this work have to come from somewhere. It comes from the internal energy, from the kinetic energy. It comes of the gas molecules, and in this way the air gets cool. This is why your fridge is cooling nicely. This is why the aircon is working. Although the aircon is not so nice, it's much healthier you to cool yourself with a fan. If there is no fan and there is no aircon, what you can do is make sure that you're opening such a windows and doors in your house, so at one place where it's hot, the draft will come to the other place. My house is a gift of God to me, and it is incredible that it's built in this way. And one of the places is hot, the other one is cold. So during the hot summer days, I open the doors, and it's actually better than the fan, better than the aircon, better than anything. Creates draft, natural draft. Okay, now let's go to my next question. There you see this warming of food. While we're on the food problems, I want to ask you, why the microwave warms the food, but it's not warming the ceramic or the dish that you're warming it, you know, the plastic? Why the plastic is not warmed, or the ceramic or the glass, but the food inside is warmed? Why? Definitely because the microwave works as giving energy to the water molecule, not to the molecules of the glass, or to the molecules of the plastic, or the polymers in the plastic, or in the ceramic structure, ceramic molecules. It doesn't. It does only acts on the water molecules, because the microwave has a specific wavelength where you start rotating the water molecules, and there with faster movement creates more kinetic energy, hot. This is why the microwave works to the hot food and not to the ceramic. The microwave is not working on these stuffs. Then another question which I would like to ask you, why the pressure cooks faster? Press pause. Because it rises the pressure. When it rises the pressure, we know that the bigger pressure, watch the lecture with the phase diagrams, the bigger the pressure, the higher temperature we need for the boiling point of evaporation. So with the higher temperature, the food boils faster. This is why the pressure cooker works faster of cooking the food. Then another question I want to ask you, this is familiar picture to you. Now you've got a pot, and you've got a boiling water, and then you've got jars full of water. Why the water is boiling there in the pot but not in the jars, although both temperatures are 100 degrees? Definitely the answer is because of the latent heat of the water. When the water reaches 100 degrees, the hydrogen bonds are not yet completely broken. We need more energy to break them completely. Although a lot of them are broken, we still need to put more energy to increase enough the energy so that they can start flying away. So this is why what's happening is that when the water is boiling in the big pot, it reaches 100 degrees, then because it's on the pot and because the stuff is on, it gives the additional energy. It reaches 100 degrees, it carries on until it reaches that big latent heat phase, until it reaches the point where you've got sufficient energy and they fly away. When they fly away, there is nothing to warm the jars in the pot. So the jars in the pot cannot get this extra energy from the water, but the pot cannot give more energy. It can give only heat up to 100 degrees transfer of heat, up to that energy. And because there is no more energy, they don't get boiled, they don't get fly. Now let's go to our new material now. We revised some old material. Now let's go to our new material. And what you see here is a graph of the periodic table ordered in their height in 3D, you can see it, by their electron affinity. What is electron affinity? Definitely something that, like I explained with the story with the salt, chlorine, female, got more affinity to the male sodium. So it pulls the electron. So the electron affinity of an atom or a molecule is defined as the amount of energy released when the electron attaches to a neutral atom or a molecule in the gaseous state, to form an anion. Anion means negatively charged particle. So now, that's electronegativity. Look at it, it is very similar to another qualities of the chemical elements that we studied. But you mustn't get confused. And that quality of the chemical elements when they combine was electronegativity. You remember Linus Pauling, which lived such a long life? He discovered it, and he says that you need to take every day 2000 milligrams, that means 2 grams of vitamin C if you want to be healthy and not sick. And that's what he said. It's not working, let me tell you, but you can try it. You may get the kidney problems though. That's definitely not the reason why he lived so long, but he said so, and he's a Nobel Prize winner, so you know he's authority. I'm not a Nobel Prize authority. So electronegativity, if you remember, was the property of an atom in a molecule. In a molecule now we've got to pull electrons towards itself more. And you can see also in this graph, you can see the elements here that were more electronegative in the molecule. They also, you see, they've got also very high electron affinity. Electron affinity was the property of the element to pull electrons to itself. Actually, it's properly says it's the energy that's released when the electron makes neutral atom or a molecule makes it anion. That means there is an energy release when there is a connection between this electron and this atom. So now, or a molecule. So what's happening is because it's a release of energy, that means this is with lower energy than it is, like I explained you before. If you take a stone high or put it in your head, if you drop it, it's gonna, if it stays there, it's unstable, it's gonna fall down. There is a lower energy. So they get attracted, the stone get attracted to the same thing, electron affinity. That means the electron is attracted to this atom, and the atom is also attracted to this electron. This is why they became connected. And this is electron affinity. Now, I said it so quickly, But now there is a very, very big consequences on that, and we need to go through these consequences. It's going to be a little bit hard science, but it's worth carrying on. Otherwise, if we're talking only about the beach and Mrs. Chlorine and Mr. Sodium, that's going to be only a soap opera. Now we're not doing soap opera here, we're doing science. So let's do science. Look at it, this ship. It's exactly the same ship that I showed you in the beginning, but just this ship is very nearby. All right, now I zoom it so that you can see it. Now look at it now. This ship, right, it's rusted, man. You can say, hey, you see a rusted also, the water is gonna come soon there inside, huh? And it's gonna drown the ship down. It's gonna sink him. Can you imagine, huh? Why this ship start rusting? What makes it rust? Every child knows that there is a rust, right? And the rust is, if you wanna believe me, $2.7 billion. $2.7 billion it costs the rust damage in a year. 2.7 billion. So there is a rust, and we need to cope with this rust, and we need to find a way to cope with this rust, otherwise the ship is going to sink. So how are we going to cope with this rust? So first, let's go through the process and how the rust actually happen physically. Just physically, then after we're gonna go chemically. Although I said to you the words of Hitler that the physics eats the chemistry with a spoon. We're gonna eat it also with a spoon, don't worry. First, let's go to the physical properties. Now let's make 4 different experiments. You've got a tube, you've got a glass tube, you've got distilled water, that means there is nothing dissolved in there, and then you've got air. We close the tube, there is air, and there is a distilled water. We don't put salt there, because if we put salt, it's gonna go like a Titanic. It's gonna go much faster. It's going to turn into rust. But we put distilled water, and you can see that the nails start rusting. Right. Then we take a second tube, and we take a dry air, completely dry air, and we put also calcium chloride, which is anhydrous. That means normally calcium chloride is very hygroscopic. That means it attracts a lot of moisture, and we put calcium chloride there to attract even the little molecules that are left in there. So it attracts the molecule, makes the air completely dry. There is no water in the air, there is no moisture, and as you can see, where there is no moisture, when it's only dry air, no water vapor or molecules, the air does nothing to the nails. Actually, you can see the nails stay without rust. Okay, can we say that the water is actually causing the rust? There is no water and there is no rust. 100% of the people will say yes, water causes rust. Now, don't fall into the logical mistake. We as humans have very hard time finding the reason of any phenomena, of anything that happens in nature. And we as humans make 5 methods to find out why something happens. The second one of these methods is called the method of differences. That means if there is one factor in one of the events, and the absence, the difference of this factor with the second event, but the event is not happening, there is no rust, that means the absence, the difference is actually the reason of this event, the reason of the rust. Therefore, the water being absent there and there is no rust, the water is the reason of the rust. Can we make this conclusion? No, we can't, because there is other factors. It's just like the farmer, there it says, look now, I didn't water my plants and they died. Then you water them and they died again. And then he said, hey, what's wrong? Now, he forgot to fertilize them. You see? So now, when we've got a multiple factor process, we need to know all the factors, not the difference of one factor that is missing in the other one, and then we can conclude there is no water. Oh well, there is no rust. Now let's make the third experiment. You're gonna see why. Now in the third experiment, in the third tube, we put water and we put nails. We boil the water, because when we boil the water, as we study, we actually remove any dissolved air, simply because the molecules that are boiling faster, the dissolved air is connected with what? With my previous questions, dipole-induced dipole. And the other one are connected in what? With hydrogen bonding, which is much stronger than the dipole-induced dipole. Therefore, when you start moving, hits the molecule that is connected. These two parties that are connected, hits it and breaks this bond, and the oxygen flies. I'll show you in the next lecture. So I'm going to show you how, when you boil the kettle and if it's transparent, first you're going to see a small bubbles. This is actually the dissolved gas. So now when we boil the water, boil distilled water, there is always dissolved oxygen, nitrogen and other gases in the water. There is always. But when you boil it, this water, they get released, because as I said to you, this dipole-induced dipole is broken of the faster movement of the molecules. So now what is happening here? We took the water out of the oxygen and basically of all the gases. Now we put there layer of olive oil, and we put this layer of olive oil to prevent the air which is in the tube. On the top of that, we don't have dry air, we just have a normal air in the tube, and this air cannot go into the water, gets dissolved, right? Because if you leave the water again, it's gonna get dissolved, because the pressure actually of the air is called the Henry law. We're gonna study it. The pressure of the air pushes the oxygen molecules into the water. They get dipole-induced dipole connection, and oxygen is dissolved in water. This is why the fish breathes, in my previous questions. So now there is no oxygen in the water, there is only water, and again, look at it. Look at it. It's not rusting. Why it's not rusting? We just conclude from the difference between the first and the second experiment that actually the water causes rust. Now we put water, and there's no rust. There is air. The air doesn't cause the rust. So now, look at it. It's not that stupid. It's not the science stupid. What's happening here? In the first experiment, we showed that the water caused the rust. Then we put no water. We definitely prove it. The water causes rust. We put air also there, but there is no rust. There is no water, no rust. Now in this experiment, we put as much water as you want. You can see it's covered. It's not even half. It's much more than this. But now we don't put air, and it's not rusting. We remove actually the air from the water. So now the air, we saw that is not causing the rust. But now we saw here also that the water is not causing the rust. The air is not causing the rust. Proof there, definite. The water is not causing the rust. Definite here by this experiment. So what on earth is going here? There is a rust here, definite. So what's happening? Now do you see? Now when you make a fourth experiment, when you put pure oxygen and we put distilled water, or like in the first experiment, right, you put air and you put water, the pure oxygen, this is dissolving in the water. Also the air, which is 20% oxygen, is dissolving in the water, and the combination between air, the oxygen, and the water, both of it causes rust. One separate one is not happening. One of them, as you can see, the dry air doesn't cause rust. The distilled water is not causing rust. Only the combination of both. And when we enforce that by putting pure oxygen and distilled water, now we make it even faster. Because now we make it 100% oxygen, not 20%, 5 times more. So now, what is happening here? Now it's going to go to the hard science, and I would like your attention. It's not so hard because I'm going to explain it. If I don't explain it, then it's a different story. But I'm going to explain it. You don't need to worry. Now, how the rusting actually is happening? What's actually happening in practice? Look at this diagram. You've got oxygen from the air. You've got iron from the nails. You've got water. And then we've got rust. This is the formula of the rust. We have rust. So we've got oxygen, and we've got iron, and we've got water, and then we've got rust. So what's happening? When the iron, right, the iron atom goes into the water, it becomes ionized, right? They lose electrons. So the iron loses 2 electrons. 2, can you imagine? And they start floating around. Now the ion is ionized. But as you can see, every ionized thing is, now it's positively charged. It tried to get connected with something. He immediately gets connected with the oxygen, which is very reactive and has a lot of affinity for electrons. So the electron gets stolen by the oxygen. So the oxygen steals the electrons, which is underwater because he releases them. When iron gets into the water, it releases the electrons. The oxygen with high electron affinity takes them away, right? Gains electrons, along with the water molecules, forms hydroxide ions, OH minus, that's a hydroxide ions, and that's what's happening. The ion, this is a simple formula, I'm giving the long way. The ion gets connected, the ions gets connected with the hydroxide ions. They form iron hydroxide. This iron hydroxide doesn't finish there, gets connected, further reacts with the oxygen, and then it forms ferrous oxide, which is rust. Do you see now? Now what's here to do with water? Water is a catalyst. Catalyst means a substance which facilitates faster reaction, lowers the activation energy of the reaction, right? Lowers it, and facilitates the transfer of the electrons and the movement of ions. You've got a catalyst in your car, right, made of platinum, which takes nitric oxide and carbon monoxide and turns them, combines them with, makes them nitric dioxide, and all of these gases, turns them to the more harmless elements, like substances like a carbon dioxide from the carbon monoxide, so we don't get poisoned by the fumes of the car. That's catalyst. Platinum works as that. This is why a lot of people stealing the exhausts and get the platinum and sells it. That's another terrible thing. But here the water is a catalyst, and as you can see, as a catalyst, the water is not destroyed in the reaction. The iron is consumed in the reaction. The oxygen is consumed in the reaction because we've got a new substance. But the water is not consumed in the reaction. So these things that facilitate the reaction but is not consumed in the reaction, actually the water is used and then after is regenerated back. You see it? And this is why we've got this beautiful chemical formula. So now what's happening? The iron is oxidized. Oxidized means losing electrons, and reduction, the oxygen gets reduced. That means gains electrons. This is why it forms the OH minus, the hydroxide ions. Hydroxide ions they get reduced, although reducing is an obsolete term, but it's now it's in the practice of chemistry, so we can't take it out. Reducing means gaining electrons, oxidation means losing electrons. Oil, rug, oxidation is losing, O-E-L, reduction is gaining, R-I-G. Oil, rug. You can remember it in this way. You can study it further on. So let's go through that. Now, if you look at the formula, I just want to point to attention. Is the formula balanced here? Now we've got one atom of iron, and then we've got two atoms where the second one came from. Then we've got two atoms of oxygen, but then we've got three where the third one came from. Definitely this formula is not balanced, so we need to balance it. How do we balance chemical formulas? We need to study that as well. Look at it. Let's study it. What's happening then? We need to put more molecules so that we can have a balanced equation. So what we're going to do, we're going to put 4 atoms of hydrogen, and we're going to put 3 molecules of oxygen gas, because you know very well oxygen is not monoatomic like we studied with the noble gases. The oxygen is diatomic, like all the gases excluding the noble gases. They're monoatomic, but the all other gases are diatomic, including hydrogen. So now we put 3 molecules of oxygen molecule, and then after we've got, let's count now, 4 atoms of iron. Let's see now, 2 by 2 is 4. Okay, it's fine. 3 molecules of diatomic oxygen. 3 by 2, 6. 2 molecules of rust. That means in 2 molecules we've got, in 1 molecule we've got 3, in 2 molecules we've got 6. So now it's balanced reaction. This is how you balance reaction. For a homework, I want you to balance the reaction between diatomic hydrogen and diatomic oxygen. I want you to balance that reaction. Right? Did you balance it? Good. So what's happening is, if you did this answer, you did it right. You've got 2 molecules of hydrogen combined with 1 molecule of oxygen. So now you've got 2 molecules of water. 2 by H2 makes 4 atoms. Let's check up in the water molecule. One water molecule has 2 hydrogen atoms. 2 molecules got 4. So it's fine, it's balanced. And let's see the oxygen now. Oxygen is a gas, O2. Now in the molecule of water we've got only 1 atom of oxygen. So when you've got 2 molecules, you're gonna go. So the balance now. Now we're fine. Now let me tell you that salt can accelerate this reaction. Why the salt is accelerating this reaction? Simply because it releases more electrons and more charged particles in the water, and now they make the process of even faster. Actually, by the way, did you know that actually you can make a light shining if you've got salt dissolved in water? It must be very salty solution. So what you do, you take piece of copper and you take piece of zinc, you put them in the glass, connect them with wires. They mustn't touch, they must be just in the water but mustn't touch. Take a piece of zinc, take piece of copper. If you don't have zinc, what you do is take a cardboard and take a penny, but must be copper penny. Connect them there and stick them in the water, and to connect them with a light, the light will shine. because there is a movement of charged particles. You see, that's excellent. So the salt makes movement of charged particles and makes the rust. It's even faster. So now let's go to the rust. What you see there, this ship that was actually rusting, and I'm telling you, if they don't take soon too much things, is gonna get destroyed. So now what is there is a several way of protection. You heard about galvanizing, you heard about electroplating, which is good, but I want to show two ways of protection of rust that maybe you don't know. One is called sacrificial protection, and this sacrificial protecting is actually a method of rust protection in which blocks of reactive metal, zinc is more reactive than iron, right, are attached to the iron surface, just like here. It's attached to the iron surface, to the hull of the ship. So now zinc or magnesium, they are attached to the oil rigs or to the ships. So these metals are more reactive than iron and will be corroded in the preference of iron. How does it happen? How does it happen? The zinc gets ionized when you put them in the water, right, and releases electrons. The zinc gets, when it's ionized, when you take electrons, you make it a positive. The iron also gets ionized, right? So what's happening? The iron, because zinc is more reactive, it releases the energy, the electrons in the water. Iron takes them. So the iron is not getting oxidized. It's not losing electrons. When it's not losing electrons, the iron is not gonna get ionic. You're not gonna have the ionic form that we studied, 2 plus, iron 2 plus. So it's not gonna get a positive ion. When it's not positive ion, there is no way to react with the hydroxide ion to make iron hydroxide, and then after turn more oxygen and turn to iron oxide, which is rust. It's not gonna rust. You see all of this process. Please stop it now and go back and listen it one more if I talk too much, too quickly. So the zinc releases electron. The zinc, though gets ionized, reacts now with the hydroxide ion, reacts with the oxygen in the water, and gets corroded. It gets eaten up. But the ship is not corroded and gets eaten up because you've got the electrons actually get into the iron. And why they get into iron? Because iron is less reactive than the zinc. Zinc is more reactive. They go. So the zinc acts as an anode and the iron acts as a cathode. So the iron attracts the electrons from the zinc and it doesn't get corroded because it stays in its neutral form, doesn't get ionized. That's a brilliant way of protecting it. Now, question, I've got a question for you. Please listen to me very carefully. Why when you've got zinc coated tin, even if you scratch it, it's not rusting? Why? I repeat, why if you've got zinc coated tin, like in the kitchen, like in your roof, you've got special corrugated roof which is zinc coated, why if it's scratched it's still not rust? But if you've got galvanized or electroplated, worse even, the tins that we use in the shops for conserved food, like a tin tomatoes or tin beans, they're electroplated. It's the cheapest way because zinc is expensive. They're electroplated, and galvanized is even more expensive than electroplating. They're electroplated, but if you leave tin in the garden, it's gonna get rusted. You can see it, although it's electroplated. Why? And why the zinc coated? Why zinc coated tin or whatever surface is not rusting? The reason is what we studied. The zinc is, when it gets in contact with air and the water together, we said that we need air and water together, or a moisture in the air, or dissolved oxygen in the water, then it gets ionized, releases electrons, and these electrons goes to the damaged surface where is actually the naked iron, the iron actually gets them, and the iron still stays neutral, doesn't get ionized. This is why zinc coated tin is much better than galvanized and electroplated. Electroplated is very bad, but I mean it rusts quickly. One single scratch or whatever damages the surface, and from there peels off completely. All right, that's one of the things that is responsible for protection of the ship. And this obviously, this ship didn't change his zinc bar of yet any, so it started rusting. The one that I showed you. When you've got little rust there and there and there, what you can do is you can do also sacrificial anode by aluminium, and that's a steel. All right, so now what you do, you pour boiling water, hot water on the steel, and then after, you see you've got little spots of rust. You see how they go, because aluminium is more reactive than the iron, and I explain you how it works. But this is practically actually how it works. You can see now aluminium oxide is very good protection. As you can see, start reacting this black stuff, and it's gonna protect your zinc if you've got some little spots like I did it. Just put hot water, boiling water, and then take the aluminium foil and then rub it. If you've got bigger structures, you see there is the rust. If you've got bigger structures, then you need more efforts. So it looks like a galvanizing, and you have to do it from time to time, because the aluminium is going to run away, maybe, you know. So that's it. Otherwise, you have to leave a piece of aluminium. So when it gets wet, the cathode is the steel structure, and the anode is the aluminium. Aluminium is gonna get sacrificed. Now let's see the other way of protection of iron. Other way of protection of anything that got access to water and to air together. Otherwise, by itself, it's not gonna work. It's called electrolytic protection. What you see here. Now, can you imagine the oil rigs? That's the oil rig here that drills oil, and that's a steel frame, which is iron. Now, if it's a stainless steel, it's going to be much more expensive. If it's built with aluminum, it's going to be even more expensive. It's very expensive, but it's built with iron. So why it's not rusting? Because if it starts rusting, all of this is going to collapse. All right. How all of this bigger structure is not rusting and therefore collapsing? One of the ways what we studied is the sacrificial protection. The zinc gets sacrificed to protect the iron. The other one is electrolytic protection. So what's happening? We make it like a electrolytic cell. What means electrolytic cell? We've got power, electric power, which moves electrons from the anode to the cathode. So now they go to the cathode, and as you explained you before, the electrons coming from the zinc before went to the iron, and the iron didn't get oxidized, didn't lose electrons. Same thing here, just we put it with the electricity. We put power source, the anode we connect with the titanium anode, the cathode we connect the steel structure, and what's happening? The electrons move from the titanium. Obviously the titanium is going to get corroded, but we're choosing titanium especially well. We don't choose zinc or copper or whatever other more reactive than element than iron, because titanium is one of the elements which is much less prone to corrosion than and to rust and to oxidation than any other element. So it's very stable element, and is less corrosive. it's actually inert, but still is going to get corrosed because we're moving electrons from here by electricity. The electrons get attracted by the positive part, right, by the anode of the power. The anode turns there, the electrons start moving, goes there, so they go to the negative part. So now titanium gets ionized. When something is get ionized, it gets very quickly reactive. The nature doesn't want ions going around like this. They want to get connected. The ions in the water is a different story. They are surrounded by the water. But you see there, the titanium, when it gets oxidized, is going to react with the hydroxide on same story. We're going to have rust. Now I'd like you to look at the right bottom corner of this diagram. Now you've got seawater that contains different anions and different cations. The anions are the OH and the chlorine, and the cations are hydrogen and sodium. Now, sodium and the chlorine, they are spectator ions. They don't actually participate in the redox reaction, in the reduction oxidation reaction. Now, when we learn this lecture, can you tell me now why sodium ions and chloride ions don't participate in this rusting reaction, although they may speed it up as we study? Why? Why they are spectators ion? Press the pause. Of course, because they are very soluble. You can see very well that the ion dipole reaction makes them very soluble, so they don't participate in the reaction of the redox reaction. But hydrogen and the hydroxide ion, actually they participate in the reaction. What's happening is that the hydroxide ion is the bad guy. This is the one that causes corrosion, and this is what that's going to eat even the titanium, because the titanium obviously have to get sacrificed to protect the steel oil rig. Hydrogen is not bad at all, because it's a positive ion, goes to the cathode, and at the cathode he gets reduced. That means he gains electrons. Now he becomes hydrogen atom, not hydrogen ion, and then it bubbles up, and then you got hydrogen gas. Or he's gonna get combined with the water, creating a different ion, but it's different story. The most important thing is that you must realize that here you've got spectator ions like sodium and chlorine, and then you've got active ions in the reactions, which are the hydrogen ion, and especially the bad guy that causes corrosion is the hydroxide ion. So the other thing titanium anode is selected is because it makes a protective layer on itself with titanium oxide, and that's what is happening. Now, if you've got choice to buy aluminum fans or iron fans at your house, all right, what will you choose? Obviously you're going to choose aluminum fans, because why? The aluminum is very reactive. All right, the aluminum is very reactive. It's actually more reactive than iron. Why then? The iron gets rusty, your iron fans get rusty, but the aluminum doesn't get rusty. The aluminum, being more reactive, is doing exactly like the titanium is doing. And aluminum quickly forms aluminum oxide on top of the surface. Gets oxidized very quickly, but that's not rust. Iron oxide is rust, but aluminum oxide actually protects it. And that's very good for protection. And this actually prevents corrosion. That's very important. You to have aluminum fans than to have iron fans. So that's excellent. It's going to last you more. It's going to cost you more, but it's going to last you more. The other one is going to disintegrate because in the air you've got moisture and you've got also oxygen. Even if you're in the desert Sahara, you still got moisture and you still got oxygen. It's going to rust. It's not going to rust like if you're in the beach. This is why beach properties, you can see their iron fences and their iron structures get destroyed much faster than the one that are dry, but still is going to get oxidized and still is going to rust. Now, how can you protect if you've got some lock rusting and you have to pay another money every year for another lock, or some piece of iron that you need to protect, but it's not so big, you know, like a fence? Then you need to buy aluminum fence. But if it's not so big, it's like a lock or some other pieces, what you can do is cover it with grease or cover it with Vaseline, because it will stop the access of oxygen to the iron and will stop also the moisture to the iron. And you know very well that the water is catalyzed the reaction, and the oxygen is actually reacting with iron, and you're not going to have both of it, and you're not going to have rust. So smear it with Vaseline and smear it with grease. So I think it's a nice time to stop here, to look at our ship here and tell the captain to get some zinc, put it in a hull so that you can have sacrificial protection. And now we know how to protect ourselves from rust, and also we know how the water reacts. We know many other things. Now this lecture was heavy, I can admit, a lot of information. I'd like at least once go back to it and study it. And I hope I'm going to see you next time. Promise you're going to study.